I'm Brett.
I'm Emma. I'm Gabby.
And I'm Quade.
And we're here to talk to you today about systems in action, and more specifically, an example of machines and mechanisms. So to start us off, the first thing we need to ask is, what is a system in action? So next slide. Right there. Awesome. So yeah, as I said, we need to ask ourselves, what is a system in action? And a system in action is a group of physical parts that work together to perform a task. Overall, it's the series of events in a system and how each system state changes. So to be a system in action, there are three main requirements. First are the inputs, then there's the system states, and lastly, the outputs. So when input is intaken into the system in action, then the system states are used in order to use human and natural resources to produce a wanted output. So now that I've given you a brief explanation of what a system in action is, we have a quick poll question for you, where we want you to try and see if you can figure out which of the following are examples of systems in action. So if we head to that poll question now. Awesome. So as we can see, we have an example of a school, a bicycle, a city traffic system, or are all three examples of systems in action? So we want to hear what you think. Awesome. So if you selected all of the above, you would be correct. So all three examples here that we have posted, a school, a bike, and a city traffic system, would be a system in action. And you might be wondering, why is that? And that is because of the three requirements that we stated on the last slide. So all three examples have inputs, system states, which are also known as components, and outputs. Next slide. Awesome. So one of the main goals for our presentation here is to try and get the point across that systems and actions are all around us. And to start us off, we want to provide an example of a system in action in society and in the environment. So as you just saw in the last slide, an example of a system in action would be a school system. So let's consider this. Let's consider I am walking to school on a Monday. I'm walking in, just had a good weekend, just walking through. What is that, Quade? Quade, how was your weekend?
It was good. Good. How about you?
You know what? It was all right. Did some origami, did some karate in the garage, just the usual weekend.
That's pretty good.
Okay. Oh, ding. Is that a bell? I'm gonna be late for class. Let's go.
Gotta
get to class. Boop. Roll up to my desk. Ready to learn. Pulling out my pen and paper. And then in class, our teachers, what do we got today? We got some math, we got some English, and we got some science that we're learning. Awesome. So day goes on. Go out to recess. Come back. Learn a little more. And then ding. That's the school day. Now I'm heading out, tucking in my chair, and heading home. So for this school system, the students, such as yourselves, would be the inputs. In my first interaction with Quade, that would be a student-to-student interaction, and that would be the first component of the system. And then as well, when I go into class and we're talking with our teachers and having lessons in math and science, that would be a student-to-teacher interaction, and that would be another system state. So what would the outputs be of these? From the student-to-student interaction, an output would be either communication skills or gaining friendships, while from the student-to-teacher interactions, the outputs would be learning knowledge on science, English, and whatever we learned for that day. So now moving on to an example of a system in action in our environment, we would have a beehive. So if you want to, awesome. So for a beehive, the inputs would be the bees, the pollen, and the nectar. And as you can guess, the nectar collection would be the system states, followed by the conversion of nectar to honey. And then, as you can guess, the output would be the honey for that system. Awesome. So now that we've seen that systems and actions can be shown in society and the environment, what we wanted to do to kind of hammer home the point is we created our own system in action. So what we did is we built a model of a hydroelectric generator in order to show component by component how we can produce in the real world a wanted output. So we have a quick video to run you through our system here. So now I'm going to bring in Gabby, and she's going to explain the first part of our system.
Awesome. All right, guys. So like Brett said, I'm Gabby, and I'm going to explain the first two pieces of our system. So the first piece of our system is our input. So like you might have saw in the video, we had a big water tank on top. So that is what supplies our system with input. And then we have a valve with a knob. So that is how we determine how much input is being put into the system. So some other examples of inputs could be electricity, people, mass, some sort of energy, but in our case, it's water. So after we turn the valve, the water is acted upon. Now you might be thinking, what acts on the system or on the input, really? Well, nothing acts before the input because it's the first thing in our system. But after it comes out of the valve, we act on it with gravity. Next slide. So in the next slide, you'll be able to see that we have kind of a pan video of our input system. All right, perfect. So in our next slide here, we'll be able to talk about how gravity works on our system to bring the input in. So like you and me, water has mass. So when we jump up in the air and we come back down, we accelerate towards the ground with gravity. Now, gravity acceleration rate is 9.8 meters per second. And you might think that's not very fast at all. 9's not a big number. But if you were to think of driving a car from Guelph to Toronto and accelerating at 9.8 meters per second the whole time you were there, you would make it to Toronto in only 4.4 seconds. So it is really fast. Yeah. So when something like water or like you and I have mass and we accelerate towards something, we have something called force. So when the water comes out and accelerates towards the water wheel, it hits the water wheel with force. And the force will continue to turn the water wheel in a rotational motion. So we'll see that again on the next slide here. So we have mass, it's hitting the water wheel is turning. Another example of this would be like when you're at the beach. If you're running into the water and you get hit by a big wave, it could push you over. So it's the same thing, water exerting a mass on person or a thing. So next we're gonna bring in Quaid and he's gonna show you how this rotational motion turns into the gear component of our system.
So as Gabby said, we have this wheel that's spinning here. Now, we want to do something with this rotational motion. So what we do is we put it through this gear system here we see in red, and we have a quick video to show you for that. We have these two wheels here, right? One of them is much larger, and one of them is much smaller than the other. And they're connected by a string. And so this essentially allows us to turn one wheel without the wheels actually touching each other. I mean, the string is touching, but the two wheels themselves are not touching. And so we have this water wheel spinning. That spins the larger gear, which then is connected by this string, which turns the smaller gear. This is essentially the same idea as the sprocket system or gear system that's on your bicycle. You know, you have some gears on the front, you have some gears on the back, and it's the same thing that's happening here. So now on the next slide, I really want to dig in to how this works and why we do it to give us an advantage. So the core idea is that the wire connecting the two wheels is always moving at a fixed rate. Okay, but since this second wheel is much, much smaller, as that string rotates and moves around, it has to travel a smaller distance on the smaller wheel than it does on the larger wheel. So ultimately, since the second wheel is much smaller, the second wheel turns much, much faster, and we get a faster rotational motion. This becomes incredibly important for our next system, where the speed of rotation is important to how well it works. So I'm going to bring Emma on, and she's going to explain the next system.
All right, so the next component of our system is the generator, and this is composed of a magnet on a rotational axis surrounded by copper wire. Now, this magnet is on the same axis of rotation as the smaller wheel Quaid was just talking about. So as this smaller wheel turns, it turns the magnet, which then creates a magnetic field which acts on the wire and produces an electrical current through the wire. And this is called induction. And we have a video to show you exactly what's happening here. All right, so we just saw that the magnet spun within the copper wire and created current through the coil. Now, if we go back to the very beginning of our system, to the water has potential energy. And when it falls down through here and hits the rotating wheel, it turns into kinetic energy, which is then sent through our whole gear system and then the magnet, which then converts this kinetic energy into electrical energy in the coil. And then I'm going to bring Quade back in to talk about the next part here.
So since Emma explained, in this generator, we're creating electricity. Now, we want to do something with this, obviously, right? So we have the generator creating electricity, and we want to move it to somewhere else and do something with it, make something usable out of it. So what we need to do is connect it by wires. You know, electricity flows along wires. So what we have here are two wires connecting the generator to our model city. And this is essentially the fourth component. There's details as well in there where you have certain amounts of losses in terms of energy. So it's an important point to consider and must be included. This is the exact same thing you would see in a large-scale system in the real world. So usually the wires that connect the power plants to our cities are the large metallic triangular power lines you see kind of out in the country. This is because the voltages and the amount of electricity is much, much higher. There's quite a bit of detail and quite a bit of technology involved. And it's also important to note that there's a safety issue with this. So we're dealing with relatively small amounts of electricity, but it's important to be important to consider the safety and never use electricity without supervision. So now I'm going to bring it back to Emma, and she's going to talk about what we actually use the electricity for.
Okay, so if we go to the next slide, we use the electricity to create our output, which is electricity and power generation, which we saw in the original video to power the little lights in our model city. And if we go to the next slide, we can see the video up close and personal. In this video, we can see the little flashing lights in the houses, and that is caused by the rotation of the magnet. So each rotation of the magnet causes a flash, and yeah, so we can see that there. Then I'm going to throw it right on back to Quade.
Okay, so on our next slide, I want to bring this whole system together. So we saw everything. We saw initially what Gabby talked about, which was this bucket of water that fell on the water wheel, making it turn. And we saw that the water was our input. Then, through a series of gear systems and a generator, we were able to get an output. So we saw that the gear system was able to create our mechanical advantage. Then the generator was able to convert that rotational motion into some sort of electrical energy. Then that electrical energy was transferred along some wires to our city, which was ultimately our output. This is the exact same idea as a real large-scale hydroelectric generator would work, but instead of a bucket of water, you might have a dam, a river. A key example of this is Niagara Falls. And on the output, you would have not only lights, but everything you use electricity for. So now that we've seen kind of how this whole system works together, I want to pose an idea. We want to ask you guys, how could you change the system to improve or increase the output? So how could you change it such that you get more electricity out? And so we have a poll for you guys. So which of the following would optimize the system and produce a larger output, more lights in the houses? Would you add another gear system exactly like this? Would you reduce the force on the water wheel? Would you increase the force on the water wheel? Or would it be none of these? So I'll give you some time to pull that out. So the correct answer is increasing the force on the water wheel. And, well, why is this the correct answer? Well, if we increase the force on the water wheel, this wheel is going to spin faster and faster. Then that rotational motion is going to go to this and spin faster and faster. Then through this gear system, it's going to be even faster. This magnet will spin faster and faster. And then, as Emma said, the faster the magnets spin, the more electricity that's generated. So, and then we get more output here. So ultimately, more pressure, more speed, more electricity, brighter lights, and that's how we improve the output. There's also a few key details that we didn't include that could be present. So we see that the generator has a bunch of copper wires wrapped around it. What we could do is increase the amount of wires wrapped. That would also increase the amount of electricity generated for the same speed. We could also increase the strength of the magnet. That would also increase the amount of the output. But we didn't include that. So I'm going to bring it back to Brett, who's going to recap this all up.
Awesome. So just want to hit next slide. Perfect. So as Quinn just kind of gave us an example of how we can increase the output of our system, I feel like we've come full circle on the example that we wanted to show. So right now, to kind of wrap us up, I want to hit on the main points that we want you to be able to take away from our presentation today. So the first is just, we want you to have a really good and general understanding of what a system in action is. So we want you to be able to say that you know that a system in action intakes the inputs, the system states or components use human and natural resources in order to produce a wanted output. And we showed that with our system as we use the equipment available to us and then use science to help each component get us from our starting input to our final output of lighting up our community. And the second main thing we want you guys to leave with is that systems and actions are all around us. So the next time you're out and about, whether you're on the bus riding home from school and looking out the window, or you're out in the city shopping with your parents, we want you to try and open your eyes and see if you can find examples of small or large systems and actions that you would see in your everyday life. And as well, we want to further that challenge to see if you can use your creative minds to try and produce your own system in action. So whether by thinking of what outputs you want to start with and then going back to the start, then finding components that can get you from your inputs all the way to your outputs, and be as creative as you can. If you need to, maybe use a web diagram to visualize your components, or use a flow chart of getting you from your inputs to your outputs. But be creative and see what you can come up with.